Hi everyone, and welcome to the first lecture on cryptanalysis. My name is Maria Eichelseder, and I'm going to be holding this course together with my colleague Markus Schoffnegger, who you'll meet for the first time in 2 weeks. The plan for today is to have first a short administrative introduction to tell you how this course is going to work, how you get your grade, and so on. And afterwards, we're going to have already the first lecture unit on factoring. Before we start with all of that, let me give a brief summary of what this course is going to be about. The title actually already says it all. It's about cryptanalysis. But what is that exactly? The goal, or what I want to tell you about here, is primarily how to properly scale your cipher to get something secure. So in cryptography, you probably know, we very often talk about things like key sizes, number of rounds, and a variety of other parameters that we can scale our cipher with. We can choose larger or smaller keys, more or fewer rounds. And the main question behind this is always, how large does it have to be in order to achieve the security that I want? And this is essentially what the main question that all of the lectures are going to revolve around. So we are going to have a look at all of the cryptanalytic methods that determine which parameter corresponds to which security level. So more specifically, we're going to have a look at both the cryptanalysis of asymmetric crypto and symmetric crypto. In asymmetric cryptography, the schemes that we have are usually based on some sort of hard complexity theoretic problem. So what we are mostly going to have a look at in this part is algorithms for solving these hard problems. First and foremost, the factoring and the discrete log problem, but also a couple of other approaches how to break asymmetric cryptography. In the second part, in symmetric cryptography, this is no longer so clear. So in symmetric cryptography, every cipher, every encryption scheme is more or less its own hard problem, and we need dedicated attacks for this specific cipher. However, there are a number of very widely used general attack strategies that are more or less applicable to all the different ciphers. And when we design something, we always need to check resistance against all of these specific attacks. So this is more going to be the second half, or maybe the second 2/3 of this course. So let's have a look at what we are going to do in some more detail. Today already we're going to start looking at how to factor integers. So for this we will have a look at a couple of algorithms and also at a particular mathematical tool called continued fractions, which turn out to be surprisingly useful for factoring. And next week we're going to continue with the second big problem that underlies the asymmetric crypto that we use today, namely the discrete logarithm problem. And we will see that some of the methods used there are actually very similar to those in factoring, whereas there are also some differences that are particularly relevant when we look at things like elliptic curve cryptography. We're also going to have a lecture that has a look at how not classical but quantum computers can help in speeding these things up. So we will have one lecture about what quantum computers could do for us in cryptanalysis, both on symmetric and asymmetric crypto. And finally, we are going to revisit another mathematical tool that some of you already heard about last term in cryptography, namely lattices. And while we previously talked mainly about why lattices are useful for building cryptography, it also turns out that lattices are super useful in breaking cryptography. And this is what we want to have a look at. So this is the first 4 or 5 lectures. And then we switch to symmetric cryptanalysis. One of the bigger topics there is going to be different statistical attacks on block ciphers. We already met one of those last term, namely differential cryptanalysis, but we actually only saw a very simplified version of how this works. So here we're going to look at the original thing. And also see another statistical attacks with some similarities, namely linear cryptanalysis. We're also going to have a look at different techniques which are not statistical, specifically algebraic attacks, which are more related to writing down a symmetric cipher as a system of equations or as one equations, depending on the technique, and then solving that with algebraic methods. And we also, so most of this is focused on analyzing block ciphers, but we are also going to have one lecture dedicated to other primitives and schemes, particularly hash functions and stream ciphers. And this will take us up to approximately May or so this term. And at the end, we have a few selected topics, and you are going to choose what those are, because you might be the ones presenting them, if you choose to do so. So this covers topics from both of these areas, but also some additional topics beyond. Now, I've mentioned already a lot of terminology here, so if you didn't visit cryptography last term, you might be wondering what some of this is. I guess that you know at least some of that. So what are the prerequisites for this course? If you already did cryptography with me last term, perfect, you're set to go. If you didn't, you might also be set to go. So in particular, if you're studying mathematics, you probably already know everything that we need as a background for asymmetric cryptography. Some terms that I expect you to be familiar with here are terms like groups and finite fields, some basic number theory like greatest common divisor or modular arithmetic, stuff like that. And we will have a tiny bit, but just a tiny bit, about elliptic curves. If you don't know too much about that yet, or if you forgot everything, don't worry, it will only be a tiny part. In symmetric cryptography, you should know terms like block ciphers or hash functions when we start with this part in a couple of weeks. If you don't know those yet, I have a couple of links for you afterwards that you can have a look at. It also helps if you already know some cryptanalysis basics, for example, the basics we had a look at related to differential cryptanalysis, so that you're familiar with terms like key recovery and distinguishing something. Those are useful terms. So if you think some of this is missing in your vocabulary, have a look at the website for the cryptography course, because thanks to COVID, we of course have recordings of all of this stuff. And I've picked out 2 lectures here on symmetric cryptography and 2 on asymmetric crypto that would be good as a foundation if you feel like some of this is missing in your vocabulary. So this is for following the lecture. If you have specific questions and a specific background, don't hesitate to just ask me and I can give you some recommendations on what might make sense. For the programming exercises, we are going to be doing primarily what I would refer to as mathematical programming, which means we are going to need a couple of mathematical tools and functions, like things for doing modular arithmetic efficiently or finding a greatest common divisor. It's also great if you have some way of factoring small numbers or so. So there are 2 main recommended ways how you can do this. The first one, which most people have used in recent years, is to use Sage, which is essentially Python, but with a couple of, or many useful methods. And you can either install it locally, but there's also a Sage server hosted by TU Graz where you can also run your stuff. And there's also a cloud variant of Sage where you can run your stuff. So if you have some Python basics, just use one of those web resources if you don't want to install the full thing. It also works, and in some cases it might run a lot faster but be slower to program if you use C++ with some nice mathematical library, some number theory library. We will give you some recommendations on this when we get to the specifics in the lecture. Okay, so these are a few introductory things. I now briefly want to introduce the relevant people here. So you've already met me. You see here, I'm going to do approximately every even numbered lecture, except that I'm also doing lecture 1. And Marcus is going to be doing more or less every odd numbered lecture, except for the first one, and except that he also does the last one. So you'll be switching between the 2 of us every week. We have slightly different YouTube setups, but both of the lectures are going to be available in the same way. You can already find all the links to all the lectures on the course website. I'm also the person to contact if you have some specific question that is primarily relevant for yourself. For example, if you miss some registration deadline or if you have some issues doing something administrative, I'm the person to contact. If you have later questions on the specific lectures or on some of the exercise tasks, of course it's preferable to contact the lecturer who did the corresponding unit in the lecture. Now there is of course somebody very important missing, and that is you. Now unfortunately I can't really meet you, but it would be great if I could have at least some, let's say, statistical info about you. So in particular, one thing I noticed when I looked at the list of participants is that I don't actually know like about 1/3 or half of you. So I'd particularly be curious what your degree program is. If you want to show up here, just go to the URL you see on the top here and enter the code you also see on top. There's also a direct link in the description of this video below. So let's have a look at the results. So far we've only seen a couple of computer science entrants primarily. At least one mathematician. I think there are a couple of you actually. And here is a category if none of the other ones fits for you. So while we wait for the results to drop in, maybe I can answer the Cass request we saw earlier, because she's already here. So let's invite her to also analyze the results. So let's see. Okay, at least 2 mathematicians found, something like 8 or so computer scientists, only 2 telematiker or computer engineers, and 2 software managers. Okay, no international incoming students apparently. Okay, that gives me a first idea. Then I also have some idea how the next question is going to look like. So since I didn't know many of you, I was wondering, oops, wrong click, whether you actually know each other. So what I was wondering is, do you already know other people who are doing this course? And one of the reasons I'm asking is that this is going to be a team exercise, or it's recommended to do as a team exercise. So if you don't know anyone, it would be a good idea to get in touch on the links I'm going to post afterwards to see if you can find somebody. So if it stays like this, it would be an interesting result that one person says that they know several of you, but very few people can say the reverse apparently. This looks like a very star-shaped knowledge graph then. There's 5 people who say they think they don't know anyone. Of course, you don't know who exactly is registered, so you might find out that you know somebody after all later. But this looks like a pretty sparse graph that we see here. Okay, but I guess for these people it should be easy to come up with a team, and the good news is that here we have enough people to also have several freshly met teams. Okay, then let's have a look back at the course contents and some more administrative info. So when is this lecture going to happen usually? You already saw that in your calendar, else you wouldn't be here. So usually the lecture is going to be from 4, more or less sharp, until 5:30. It's always going to be here on YouTube. There is no alternative real-life version of this. You can always interact by either writing anything in the chat, this would show up on top here, or by asking a question in the Menti that you already opened. Now I think I didn't enable questions on the current slide, it appears. I will do that for next time, but I have 2 breaks or so where you can still post your questions. But if you have something that is immediately relevant to the current slide, just do so in the YouTube chat. One thing I would be wondering about is whether you prefer to have a break in the lecture. I haven't planned one for today, but for the next few weeks we can adapt to your wishes. I will have a poll in a moment for this. So if we do this break, it would be after approximately 45 minutes or so, would take approximately 10 minutes, and then the lecture would end a couple minutes later. So some people find it very hard to concentrate for more than 45 minutes or so in an online lecture, even harder than in real life. So if you're one of those people, let us know. You also saw in your calendar that there is an exercise slot right after. There is usually no fixed program in this exercise slot. I will show you later a calendar. There are a few, I think in total 4 times where we are going to use this slot for something for the plenum, so for all of you. Namely first to introduce the exercises that you're going to solve and for question hours. Otherwise, in the other weeks, we are just going to be available on demand on Discord. It means whoever the lecturer is, they will join Discord afterwards and be available there for half an hour or so for a more detailed question, which might relate to the exercises. We might also be available for voice chat there if you have some debugging issues that you need help with, something like that. And if there are deadlines, they are always at midnight, Central European Summertime, or whatever time zone we currently have. I've sort of lost track whether we have summertime or not, but whatever time we have in Graz. There are only going to be 3 of those, so 2 for exercises and 1 for team registration. So let's have a look at your preferences for the break. So the one thing I'm wondering is how much you want to break. So you can, I think, choose from 1 to 4 or something, where 4 is yes. And the other thing is that I was planning to use the Menti also for some content related stuff, not in this lecture, but in the following ones. So for example, to do a brief recap of what we did in the previous lecture. I don't know whether you like that, that's why I ask. So currently the trend is towards no break and yes quiz. Let's let it run for another couple seconds, and it looks relatively clear so far. Okay, so it looks like this is going to stay. Break rather not, so probably we don't make any then. And quizzes probably yes. Okay, thanks a lot. So both of these are only relevant starting next week, I think. I haven't prepared any quizzes for today. Okay, let's have a look now at how the exercises work. And how you get a grade. So for the exercises, I already mentioned this is going to involve programming. So more specifically, we have 2 exercise sheets, so 2 submission deadlines, and each of these is going to consist of a few subtasks. And after each submission, we're also going to do exercise interviews, Abgabegespräche, which Markus and I are going to execute. So this is going to be something like 15 to 20 minutes where we just discuss your submission, have a look at which things worked, which things didn't, and whether you understand what you did. For the lecture, you have actually 2 options of completing this course. The first option is the very classical one. You can do an exam. The second one is more of a seminar style. So if you say exams aren't so much your thing, you prefer focusing yourself on one topic in more depth, then instead you can also do a presentation in one of the last lectures. So let's have a look at some details. In the exercises, you're going to implement stuff that we do in the lecture. So we will pick several attacks for the first assignment sheet for asymmetric crypto and for the second for symmetric crypto, and you will implement those in a language of your choice, but as I said, there are some recommendations that are probably easiest for you and also easiest for us to help you with in case you run into problems. These are going to be tasks that are designed as teamwork, so we would recommend that you do it in teams of 2. If you say, I hate other people, I want to do this alone, you can do so, but really it's just less work if you do it in teams of 2. Each of the assignments that we have has 3 tasks, a relatively easy and short one, a medium one, and one that is more effort. And they're usually independent from each other, so you can start wherever you like and do whichever ones you like. The good news is to reach 100%, you don't actually have to do all of them. So if you sum up the points here and multiply it by 2, you will notice that you can achieve a total of 48 points, but we act as if 32 is 100%. So the idea is that you can simply drop one of the, for example, one of the big exercises or a small and medium one without any repercussions. This is to make the course scale better with the corresponding ECTS, and also to just give you some choice. So if you say you're a lot more interested in one of the 2 halves of the lecture, that's fine with us. The point distribution is then as usual, so if you get at least 50% of our 100%, then you get a 4, and the rest towards our 100% is divided evenly in 4-point slots. If you have questions on this afterwards, feel free anytime. When is all of this going to happen? The first one, the first sheet is going to be released in 2 weeks' time after the lecture. This day is also the deadline for registering your team. You're going to register this in the STIX online system. I have a link later. So you have now 2 weeks to find someone to partner up with or to decide that you don't like other people. The deadline is something like 5 or 6 weeks later, at the end of April, and we have one bigger question hour planned 1 week ahead of that. But as I said, after every lecture there's a small question hour where you can ask your personal questions. The second one is going to start 1 week after the first one ended, in the beginning of May, and the deadline is currently planned for 10th of June. Since the week before that is actually a holiday, I think it's von Leichnam or something, the main question hour is 2 weeks before that. If you say you don't like this, you want a last-minute question hour or so, or if you say I already have 10 deadlines in mid-June, let us know. If there is a majority for something, we can also move the deadlines around. But this is our suggested plan, and if there is no strong reason for anything else, we'll stick to it. So, how do you register your team? By just going to STIX, logging in there. You log in by simply saying you have forgotten your password, you'll get a new one. And the database of email addresses that are accepted is synced occasionally with TU Graz Online, but it's only synced if we do so manually. So if you signed up very late to the course, you might not be in there yet. So if you're trying to sign up and something doesn't work, let me know and I'll sync. And in there you can then create a team. This will give you a team ID and you can set some password, and whoever you give this team ID and password to can sign up to join your team. So one of you sets it up and the other one joins. I hope it's fairly self-explanatory. So this is for the exercises. Now let's have a look at the lecture. As I said, there are 2 options. The first one is a classical exam. Usually we had one written exam date for this, but thanks to COVID we are going to drop that, and we're just going to have oral exams. So we are planning one main oral exam date on the 1st of July, where we will have several slots available. You can pick one, and the exam is then going to be, you get some questions, total of 5 of them. You then have some minutes to prepare by yourself, so to collect your thoughts, to make some notes, and to choose which of the questions you answer. Because again, 100% is 4 questions, so you tell us which 4 of the 5 questions you want to answer, and we only grade those. And to grade them, you will talk first with me on the questions related to my part, and then with Markus on questions related to his part. And each of these is going to take some 10 to 15 minutes as well. If you want to know what approximately the questions look like or what sort of questions we ask, you can find some hints on each slide deck. But of course, in an oral exam, this is a sort of dialogue. So this is a starting point, the question, but then we talk about it, and we might get to some other related topics as well. And the exam covered usually primarily the lecture, but sometimes we also, or usually we added one question on one of the seminar talks, where you have suggested questions. The grading scheme is, again, as usual, if you reach at least 50% of those 4 questions, you're positive, and then it's again divided equally. If you decide to do the seminar instead, there are some prerequisites or some conditions on when you can do this, because the exam usually covers all of the lecture, whereas in the seminar you just focus on one topic. So you still need to demonstrate to us that you have a reasonable overview over the other topics. I see there is a question mark here. Unfortunately, I don't know what the question is or which part exactly that referred to. So if there is something specific you want to know, please let me know, or ask in a moment when we come to the Menti question part. The first condition to join this is that you also do the exercises. So you need to complete the exercises in order to be able to do the seminar mode. And the other thing is that you should also be active during the lecture and seminar talks. By active, I mean you should be here more or less regularly. Of course, I can't really verify that because I can't see any of you. But I also do hope that there's going to be some interaction. Particularly during the seminar talks. So I hope you have some questions for the people presenting the seminar talks, but of course, ideally also some questions for us lecturers. Whether that's here during the lecture or whether you engage in discussions on the Discord server related to the exercises, all of that is fine. But we should have the impression that you're actually there during the semester. For the presentations themselves, you're going to do that in teams of 2, in the same teams as in the exercises. So you need to agree with your team partner on what you want to do. You can select a topic that you want to present about, also until the team registration deadline, because when you register your team, you already select your topic or you select we want to do the exam. You can also find a list of the topics on the course website. These are some suggested topics. If you have something very specific that you're interested in, let me know and I can add a topic to sticks that you can select. It should of course have something to do with cryptanalysis, but apart from that we are pretty open for topics. The presentations are going to be half as long as a lecture, so 45 minutes, and that includes time for questions. The presentation slots are also all going to be in June, or I think one slot at the end of May, depending on how many of you sign up. So we have room for 2, maximum 3 presentations per lecture slot in June. So after you've selected your topic, ideally you should confer with us to agree on what you're going to cover, to maybe get some reading recommendations from us, and each of the topics is then going to be assigned to either me or Marcos, and you can then, whenever you have questions, just talk to your responsible advisor, so to say. There is a question, yay, let's see. For the group registration, is the name of the team created automatically as it says name none? Yes, the team name is created automatically, but it's only set once you send your request to create a team. So it says none, and when you click to create it, you should get an ID assigned. I see people already know who they want to team up with, or that they want to do it alone, I don't know. Back to the seminar, so so that we have a reasonably early chance to provide some feedback, we expect that you send us at least a draft version of the slides you want to present, where we can see what you plan to cover 1 week before your actual presentation, so that we can provide some feedback and suggestions. And since the seminar talks can also be covered in the exam, please include 1 or at most 2 possible exam questions in your slides. Not too easy, not too difficult, bear in mind that the people who haven't worked on the presentation probably find things more difficult than you do. Okay, so that's for the lecture. I've now a separate COVID slide, which doesn't really tell you anything new because I've already told you anything, but just to summarize what's different due to the coronavirus. Most of it is pretty much independent of what the TU Graz traffic light says. So whatever the traffic light says, the lectures are going to be online, no recorded videos, but streaming live. The seminars are by default held in WebEx. So if you absolutely want to do it on YouTube, that's also fine, but you would need to take care of the setup, and it's a bit harder to interact. So our default suggestion would be that we create a WebEx meeting and you can present there virtually. The oral exams are also by default virtual. If there is some reason why this doesn't work for you, or why oral exams in general don't work for you, let me know and we will try to find a solution for you. The exercise interviews are also virtual. They are currently planned to be done on Discord, where we are also always available for questions. So I've said earlier that there's a question time right after the lecture. That is correct. So that is the time that we dedicate to answering questions, and where we are also available for a voice chat. But whenever you have at any other time some questions, also just ask them there. I have a link later and you can also find it on the course website. If we are very lucky and it turns out that the traffic lights are already back to green or yellow in June, then there are some optional alternatives that you can choose to do. So you don't have to, you can do everything virtual. You can choose, if you prefer, to present your seminar in an actual lecture hall, because hoping that in the future most presentations are going to be in front of a live audience, you probably have a better, you can take more advantage for yourself if you do it in a live setting. You learn more for yourself. And it's also, I can tell you, a lot more fun to present to people instead of black screen. So if you want to, you can do it live if the conditions are really nice, but you don't have to. Okay, so finally, some of the promised links. There is a course website which has essentially everything that I've just said, and specifically it also has the lecture slides of each week. Plus a couple of other links here. So if you want all the links, it's easiest to just go here. For Discord, here's an invite link where you can join the EIK Discord server in case you haven't done so yet. If you join for the first time, you will hardly see any channels because you need to sign up for each course that you want to see the discussions for. And you can do so in the Getting Started channel. There's a list of icons and you select the icon for Cryptanalysis, and then the Cryptanalysis channel will appear. There's a text channel and a voice channel. You can use both at your leisure, but we won't usually see when you're waiting for us in the voice channel unless it's right after the lecture. There's also this submission system, which we're not going to use for much, thankfully, because it's very slow. It's just for the team registration and for the final submission of your code. So that's it with the administrative parts from my side. I'm now, of course, available for more questions in case you have any. So let's give it a few seconds and see if something pops up. Can the seminar also be done alone? Yeah, so the same applies as for the exercises. It's recommended to do it in pairs because that leaves less work for you, and you have somebody to talk to, like a first level of support for all your questions. You can also do it alone if you prefer. If you do it, so if you sign up for something alone, be prepared that I might ask you whether you want to merge, but you don't have to, so you can do it alone if you like. If you plan to do the exercises in a pair and the seminar alone, please let me know beforehand so that it doesn't look to us like your exercise partner left you alone or something. If you're looking for a partner to do the course with, you can just try on Discord. So I hope that question is answered. Let's see what else we have. Can one team member do the seminar and the other one the oral exam? I guess it's a follow-up to the previous one. You can do that, but if you plan to do this, please just drop me an email so that we know ahead of time. So in particular that we also know whom to contact about the seminar then. In the past years, I can't remember that we ever had the situation that people didn't want to do the same thing, but if you do, that's okay with us. Okay, I see nothing more at the moment, so I guess that's all answered. Otherwise, we move to the YouTube version. Okay, so then we are ready to start with some actual cryptanalysis, namely with integer factorization and RSA. Let me just hide the code on top here. So here we are. Okay, so integer factorization and the RSA encryption scheme. What's the plan for this part? I first want to briefly recall why we're actually interested in factoring algorithms and give a bit of an overview about what types of factoring algorithms we know today, or at least the most important ones. And we will then focus on two versions of the first of these categories, namely on squaring-based factoring algorithms. The first one of them is going to be factoring with vector basis, where we see two members of the same family, first Dixon's random square algorithm, and then an improvement of this, the quadratic sieve. This quadratic sieve is also I'll get to that in a moment, to an overview. Okay, let's instead talk about what we are going to talk about. So the second part is going to be about factoring with a specific tool, namely continued fractions. And we will again see two applications of this. First, CFrac, which is also a development of this family of algorithms here. And second, a very different, very efficient approach, namely Wiener's attack. Now this is a specific attack on RSA, not a general purpose factoring method, but if it is applicable, then it's very efficient. There is a third or a second big type in the third chapter on factoring algorithms, namely factoring with the help of elliptic curves. This sounds a bit counterintuitive, but it's also pretty efficient. And specifically, Lensstra's elliptic curve factoring algorithm. Judging from the time, I expect that we will cover this next week, unless we're unexpectedly fast in the first few chapters. So probably the lecture will end after here. Let me have a look at the clock. Yes, I think that's reasonable that we stop here afterwards. Okay, and actually this also fits quite well with the topic of next week, so moving it there is probably a good idea. So let's have a look at modern factoring algorithms. And first, the motivation why we actually want modern factoring algorithms, or what we could use them for. And the main application is one specific, very well-known encryption scheme that you probably all know already, namely the RSA encryption scheme and signature algorithm. And the crucial part about this is the key generation of this encryption scheme, because the key for this RSA encryption scheme consists of two large random primes, which we keep secret, and their product, which we make public. And a couple of other variables, in particular the public exponent E and the private exponent, which is inverse to E modulo the Euler phi function of n. And this part here, the distinction between the private key consisting of the primes and the public key consisting of their product, is the main motivation for looking at factoring algorithms. Because if we are able to factor a product of two primes efficiently, we could get from the public key to the private key, thus breaking the security of the scheme. There are a couple of ingredients that we're also to some extent going to re-encounter on the following slides, so I've recapped it here. The first one is the Euler phi function, which gives the number of numbers relatively prime to its input. So if we're looking at the product of two prime numbers, this is simply p minus 1 times q minus 1. And there is also a very relevant theorem related to this Euler phi function. Namely, if you take some element modulo n and raise it to the power of phi of this modulus, then this always results in 1 if n and a are co-prime. And this is also going to be the basis of one of the classes of factoring algorithms that we look at. Okay, so this gives rise to the so-called integer factorization problem. So what is this problem? It poses the following challenge. You're given a number n, and you're supposed to find its prime factorization. So all prime factors that it has and the corresponding exponents. And one of the hardest cases of this problem is when we don't have this many factors, but just two prime factors. And one of the main questions for the security and the key size, so the parametrization of RSA, is now how large should n be so that the complexity of factoring n is above some threshold that we choose. Usually we're interested in, for example, 128-bit security, so we want to know how large does n have to be so that the expected runtime of the fastest factoring algorithm is comfortably above 2 to the 128 steps. That's one of the basic questions. So, and to address this, we need to know the factoring algorithms that there are. And among the fastest are the following. So this list is to be taken with a bit of a grain of salt, but in general, the fastest method that we do have is the general number field sieve, which is also responsible for the factoring records that we know. We are not going to look at this because this alone would take, I guess, several lectures to explain properly, but we're going to have a look at a closely related and also very fast algorithm, namely the quadratic sieve, which is a simpler version of the multiple polynomial quadratic sieve. So if you have an understanding of this basic quadratic sieve and some time on your hands to read up, you can also get the idea of these, but it's more complicated. And then there is a rather different approach, which is why it has a different color here, the Lenstra elliptic curve factorization method. And so we are going to look at this one here, probably next week, and a simpler version of this one here in today's lecture. And actually, if you've already done cryptography, you already know the forerunners of these methods, because the first two here are actually based or are a very, very strong advancement on top of the Fermat difference of squares algorithm that we did in the cryptography exercises. And the green one here, the elliptic curve method, is a clever extension of the p-1 method that we also saw. And both of these are significantly better, so in particular the blue category is a wholly different field actually. So a different league of performance. Fun fact on the side, this week a very well-known cryptographer has actually posted a paper online where he claims that he has a much faster factoring algorithm, which would by far beat this one's here, based on a reduction to a lattice problem. However, there is currently a lot of debate whether his estimates are actually valid, so I guess near the end of the term we might know whether I have to rewrite this slide and add another factoring algorithm here on top. If you're interested, you can search for the paper by his name. He's called Schnorr, a German name, so that you can also follow the drama unleashed on Twitter or wherever else cryptographers are talking about how valid the claims actually are, because the paper is written in a rather confusing way. Okay, so let's have a closer look at these two categories that I mentioned. The difference of squares one and algebraic group factorization. The first one is based on the following idea. So it observes that if we have a number that is the product of two primes and we want to find these primes, this is actually the same as finding some two numbers x and y, which are equivalent, so whose squares are equivalent modulo n. Or in other words, the difference of these two squares is 0 modulo n. And the very first time this idea appeared was actually centuries ago. And this is in the shape of Fermat's vectoring algorithm. And modern sieving methods, so whenever you see the sieve in a name, these are usually based on a way to find such relations much more efficiently than Fermat, who simply tried out random pairs and so random squares and checked whether the square minus n was still a square. And we're going to see three members of the family in the lecture today. So first, a very simple concept that all of the others also build on, and then the central sieving idea. The second family is based on a completely different idea. Namely, what it does is it does some computations in a group whose order is related to the modulus. So it computes something modulo n, and it does this as if the number n were a prime number. And then there are some properties we know in that case that would hold if n would be a prime number. And then we keep doing these computations until we detect something that tells us, oh, n cannot be a prime number, because something we would expect to hold in that case was contradicted. So in a particular, we try to find something that is a sort of identity if we look at it modulo one of the prime factors of n. And one of the examples of this is the Pollard p-1 method, where we assume that phi of n is n-1, but it actually isn't if n is not a prime number. And the elliptic curve method I mentioned is also based on the same approach. So also acting as if n were a prime number, happily doing computations until you crash into some problem that can only happen if n is not a prime number, and that also gives you some info that you can use to find the actual factors of n. So let's first have a look at this category here. Factoring with factor bases. So I mentioned already this basic idea that finding the factors is the same as finding two numbers x and y, such that their difference, which we can also rewrite as x plus y times x minus y thanks to binomial reformulation. And the reason for this is the following. If we have two such x and y, which are equivalent modulo n, then in other words, their difference is 0 modulo n, which means this difference is divisible by n. So what we can then do is we now have a product of two things that is n, or a multiple of n. So in other words, we have two factors that could actually be factors of n. And how do we verify this? We verify it by taking these two factors, x plus y and x minus y, and computing the greatest common divisor with n. And if we are lucky, then this multiple of n actually turned out to have part of n in here and part of n in here, and we get an actual factor p or q. So if we have this approach, the main challenge becomes finding such x and y. And in the basic Fermat algorithm, this is done in a very naive way, which means the resulting algorithm isn't that efficient. However, we will in the following see some clever ways how to find such relations. And one of the ideas how we can do this is the following. So let's ask the question when a number is actually a square number. So if we have some y, when is this capital Y some small y squared? And one of the criteria how we can test that a number is a square is by looking at its prime factorization. So assume we have this capital Y and we know all of its prime factors. How can we test whether the number is a square? Well, to be a square, every prime factor needs to appear in here an even number of times. Because then each of these, so I can then divide this exponent by 2, half of them goes in y and half of them goes in the other small y. So then in total I have 2 times this half of the exponent. So if we already know the prime factorization of a number, then we can check easily whether it's a square. And we can also easily get the square root because we simply take each exponent and divide it by 2. This is very easy to verify. One way how we can now try to build such a square number is we can take the following. We can try, so we remember that we want to find some x and y such that x squared equals y squared. So we want some x squares such that modulo n, the result, is also some square. So what we can do is we can try many random numbers x, square them, and look at the result modulo n. So far so easy, that's not so different from what the Fermat algorithm does. Because in most cases we will get some prime factorization here of this result y, which has some even and some odd exponents. However, if we have several of these relations, we can actually try to combine them, so to multiply up some of the x's, so that, for example, in this case here, 2 has an odd exponent in both, 3 has an even exponent in both, 5 has an odd exponent in both. If I now multiply these two numbers, I again have a square on the left-hand side. And if I do this on the right-hand side, combining these two odd ones gives me an even exponent. Combining the two even ones gives me an even exponent. And combining the two odd ones again gives me an even exponent. So I can create squares on this side here by multiplying up a suitable combination of non-square prime factorizations. So one of the core ideas of all of these sealing algorithms, one of the first steps, is to collect many such relations and then try to find a clever combination. And the basic algorithm that does this is the random squares algorithm that we will see in a moment. There's one issue we still have to have a look at first. Namely, we ran a bit in a circle now, right? We first said we want to factor n. Then we said, okay, to do that, let's find our x's and y's, which are squares. And then we said, to do that, we are again going to use the prime factorization of y. So this is a bit, well, circular. However, we can still do that if the factorization of y is a lot easier than the factorization of the original n. One case where factorization is easy is if we have many small prime factors. So what we can do, and what we do in all of the following cases, to factor the number y, we only test whether it's factorizable modulo a so-called factor base, which is a set of prime numbers. And if all of the prime factors of our y are in this factor base, we say that the number is smooth with respect to this factor base, because it can be factored using only these prime factors. And if we now initialize our algorithm, we usually select a reasonably small number of a set of known prime numbers, which are all not too big. And then for all of the y's that we encounter, we check whether it's factorizable using only these prime factors. And this can be done reasonably efficiently. So as an example, 864 is a reasonably large number, but it's very, very smooth. It's 3 smooth, because 3 is actually its largest prime factor. Okay, so this is going to be all the ingredients we need for our first factoring algorithm. Dixon's so-called random squares method. So I already mentioned the first step. We choose a factor base, meaning a set of small prime factors. Actually, we usually also add -1 because we're also going to deal with negative numbers. And then we collect many of the relations I mentioned previously. So we're going to generate many random values x, square them, compute modulo n, so reduce modulo n, and then check what is the prime factorization of the resulting value y. And specifically, is it smooth with respect to this factor base? If it's not smooth, so if we can't factor it using only these prime numbers, we throw x and y away. If we can factor it, we keep it. We can of course try to make it reasonably likely or more likely that the number actually is smooth. And we can do this if the number is small. Because if the number is small, then it's more likely that it has only small prime factors. And how can we generate x's such that the corresponding y's are small? Well, what we can do is we can try to search for our numbers in the vicinity of square root of n. So we take square root of n as the starting point and then some interval left and right of that. So this parameter c here tells us how large the interval is. And then if we square these numbers and reduce modulo n, we don't actually keep only the positive remainders. So if it's larger than square root of n, the result is a small positive number. If we take something in this part of the interval, below square root of n, then reducing modulo n would actually give us something fairly large, close to n. What we do instead is we look at the smallest negative equivalent number, so something close to 0 but below 0. And we get this by simply squaring the number and subtracting n. So if we do this for all our x's in this interval, we get many small values y, and likely many of them can be factored using only these factors here. And this is also the reason now why we need the -1, because some of the numbers are going to be negative. And we're going to treat -1 just like a prime number. So after the step here, we've now collected many relations of this shape here. The question is, how do we combine them cleverly? So how do we find a subset of these relations such that in the combination, every prime number has an even exponent? This can actually be done very easily. Since we only care about even and odd, we can actually represent each exponent just by the exponent modulo 2, which is 0 in case it's even or 1 in case it's odd. And what we then try to do is we try to find a linear combination of these. So I want to select some y's such that the XOR of these exponent representations is 0. If this sounded a bit abstract, I have an example in a moment. So assume that I have found such a combination, meaning I now have a subset of the x's and y's that I can combine. Then I have on the left-hand side some x, which is the product of all the small x's, and the square of this combined x is then modulo n, equivalent to the square of y, which I get as the square root of all the product of the right-hand side y's, where I can compute the square root easily by simply halving the exponent. So if I do that, I have my x and y like in the original idea of factorization. So I can now do this greatest common divisor test to test if I was successful with my x and y, whether either x plus y or x minus y has a common divisor with n, which would in that case be p or q. If this fails, I need to find more different relations and try a different combination. If I'm successful, then I'm done and I have factored my number. So the name of the algorithm also refers to this way of choosing my x's. I just choose more or less, in the original version I choose random x's, in the more clever version I choose x's in this interval here. So that's the random squares method. Let's have a look at an example. And let's have a sip of water for me as well. So let's factor this massively large number of 2769 using this tiny data factor base here, 2, 3, 5, and 7. So the first thing is we can set up our interval. So the x's are going to be close to the square root of n. So I don't remember exactly what the square root of n was. It was probably one of the middle numbers here. And we're looking at the first numbers smaller and the first numbers larger than n. And I then compute this number squared minus n. If you look at the results here, they are all positive, so this is probably the smallest number larger than square root of n. So usually we would also add some numbers on this side, so 52, 51, and so on. So these are now my candidate x's and y's. Now I need to test, are these numbers y here factorable with respect to this factor base? How do I do this? Well, the easiest way is I just take each of these numbers. I first divide them as often as possible by the first factor, then as often as possible by the next one, until I'm done. And if at the end I'm ending with 1, then I was successful, and else no. Let's have a look. So let's first divide every number by 2 as often as possible. It does fit a couple of times in here, a couple of times in here, and here. The other ones are not divisible. So then I'm left with some remainder. For example, 40 divided by 8, that should be 5, and so on. I'm not going to compute the others. Here we're already done, by the way, because 256 divided by 2 to the 8 is already 1. That's great. So we have at least one successfully factored here. For the rest, I still try dividing by 3, then dividing everything by 5, and so on. I only wrote down the largest exponent of a number that did fit in. So if it's empty, it means the number was not divisible by this, and so on. And at the end here, I'm writing the remainder that I get if I divide this number by all of these here. The numbers where I end up with 1 are those where all factors of the number are part of the factor base, meaning I have successfully collected some relations. So I have 1, 2, 3, 4 successfully found relations here. These 2 I throw away because apparently they have larger factors as well. I can now replace here each exponent by the exponent modulo 2 to just denote whether it's even or odd. So for example here, this is an odd exponent and this is an odd exponent, the others are even. So I have 1, 0, 1, 0. And for the rest as well. What I now want to do is, I want to find a combination of these here. So a linear combination of maybe this vector, maybe this vector, maybe this, and or maybe this one here, such that the XOR of them is 0. And if I do this, let's have a look. I can see that actually using this vector alone is already sufficient because all the exponents are even. But that's a bit boring. Let's do something more interesting. I think this one XOR this one XOR this one here is also 0. Yes. So let's do this combination instead of these 3 vectors. So let's take x equals 53, 54, and 57, and the corresponding y's. So I now multiply up the x's, I get some large number. I also multiply up all the y's, which I do by just taking half of each exponent. So for example, I have 2 to the power of 3 plus 5 divided by 2, so 2 to the power of 4, and 3 to the power of 1, and 5 to the power of 1, if I'm not mistaken. Oh, and I missed the 7. And in total, I get some other number here. And now I can test whether either this x plus this y or this x minus this y has a common factor with n. And it turns out we are very lucky because on the first try, this already works. So the greatest common divisor of these 2 numbers is 39, which is indeed one of the 2 factors of n. Success. Okay. So that worked well. Unfortunately, it doesn't work quite so well for larger numbers. And in particular, this step here of dividing everything by all the prime factors, this is very expensive. So it would be great if we could speed that up or do that more cleverly. And we already have a first hint of how we could do this more cleverly if we look at this slide here. You may already have noticed in the first line here, it was interesting that exactly every second number was divisible by 2. And every third number was divisible by 3. For 5, it doesn't quite hold anymore because here we have 1, 2, 3, 4, 5, 6. So the distance between these here is 5, but we have an extra positive here. So let's have a closer look at that. Let's have a look at which numbers can actually be divisible by the prime factors we're looking for. And this is the basic idea of the sieving step, to divide only the relevant numbers. So let's have a look at how this method works. The basic observation is what I just said. If we already have one number that is divisible by p, so if we have some x such that x squared minus n is divisible by p, then we can say where the next solution is that is also divisible by p. Because if we increase our x by p and square this, then the distance between the two is going to be divisible by p. So if the first one was divisible by p and the distance is divisible by p, then this result is also divisible by p. So in other words, the step size of p makes sense. If I have one solution, then the next solution p steps over must also be divisible, or is also a candidate for divisibility. And if I look at this a bit closer, I also notice I have a square equation here. So I'm looking for x's such that x squared minus n equals 0, which means there could be a total of 2 starting solutions. So let's have a look at the steps at how we do this. So we start now a bit differently. We again select a factor base, and now we try to find out which are the candidates which could be divisible. And for this, we solve this quadratic equation here. Something squared minus n equals 0 modulo p. This can have between 0 and 2 solutions. If there are 0 solutions, then this means that our prime number is actually useless for the interval we are looking at. We can throw this number out of our factor base. If we do have 2 solutions, or 1 or 2 solutions, then these are the starting point solutions where we start dividing by trial dividing by p, and the next candidate solution is p steps over. So we can, if we look at the previous example, here the first solution here, let's say, was this one here, and then every second one. Here the first solution is this, and then every third. Here the first solution is 5. The value 5 over is also a solution, and 5 over and so on. But we have a second solution of the quadratic equation, which is this one here. And 5 steps over, there is going to be the next one. And for 7 it's similar. So this is apparently the first solution, and this is the second solution. And 7 steps over from this one and 7 steps over from this one is going to be the next solution. So we know exactly which of these values we should try to divide. And this is exactly what we're going to do. So we use these starting points to decide where to divide, but otherwise we set up the table more or less in the same way. We can now try to store it more efficiently, but the basic idea is the same. And now for each of our solutions, we divide all the relevant numbers by the relevant prime numbers. So we step through each prime number and divide all the numbers by this prime number. And at the end, we continue as before. So we check which ones were reduced to 1. We keep those, we throw away the rest, and then we can proceed as in the previous algorithm. So the only difference between the two is the sieving with a quadratic equation. And sieving means we are clever in where we do the trial divisions, which for the small prime factors doesn't make that much of a difference. But once you go into the prime factors where the next step is thousands and thousands over, you save a lot of time if you divide only the relevant numbers. Okay, so this is the basic idea, and these are the two words in the sieve, in the name of this method. If you see some other sieves, then these are usually for more complicated equations here. So not just something squared minus n, but something more complex, a higher degree equation, for example. Okay, so that's already the first and most important algorithms that we want to have a look at. Now it's time for some mathematical concept that's going to help us speed this up further, or do some other clever things, namely continued fractions. So what are these and how do they help us? To see what they are, let's first have a brief look at the calendar, because you may or may not be one of the followers of Pi rituals, but if you are, you're probably celebrating Pi Day, which is in approximately 2 weeks' time, so Sunday next week, which is the 14th of March. A nice approximation for Pi. There is, however, a much better approximation for Pi that you can also find in the calendar, and this is Pi Approximation Day, which is in July, namely on the 22nd of July. And this is maybe a bit less obvious, but 22 divided by 7 is a much better approximation of Pi than this one here. So specifically, 22 divided by 7 is approximately 3.1428 blah blah blah, and thus quite close. Well, actually it's not that much better than 314, but it's also relatively close to the Pi approximation. And it turns out that this number here is a so-called continued fraction of Pi. And it turns out that this sort of approximation also works for other irrational numbers. And these are in a sort the best approximations for a number that we can get up to a specific limit for the size of these numbers here. So a follow-up question, are there any better Pi approximation days to celebrate? And of course, how is this going to help us with factorization? So let's have first a look at what a continued fraction actually is. So a continued fraction is a way of representing a real number, a positive real number. And it has the following shape here. So it writes a number alpha as the integer part of this number plus 1 divided by something, such that this here is the fractional part of the number. And this is then recursively again written in the same decomposition. So the denominator here is written again as some integer part plus 1 divided by something that represents the fractional part. And in order to avoid this complicated typesetting and be able to also typeset more deeper depth of continued fraction expansion, we usually write it in this notation here. So we just list all these integer parts, the recursive integer parts that we see here, C0, C1, C2, and so on. And if I have a number given, then I can find these integer parts relatively efficiently. For the first one, I simply round down the value I have. That's obviously the integer part. Then I take the rest, so the difference between the number I want to approximate and the integer part I have. This is epsilon. And since I don't want to represent epsilon here, but 1 divided by epsilon, I divide 1 by epsilon, again take the integer part, again compute the remainder, and so on. So if I have the number given already in a very precise way, it's easy to find this expansion. And let's have a look at a small example, namely alpha, which is 45 divided by 89. So let's just go through the steps quickly. It's very simple. We take the number, since it's between 0 and 1, the integer part is 1, the rest is the number itself. Now I invert it, so it's now 89 divided by 45, and I round down. Since this is just slightly below 2, the integer part is 1. I again compute the remainder, which is now 44 over 45. I again flip it, compute the integer part, take the remainder, flip it. Oh, and now I've accidentally actually reached an integer value. So the remainder, that is, so the distance between my approximation so far and the actual value is 0, which also means I'm done at this point. And I can represent this fraction as this continued fraction expansion. And this is precise, so 0 plus 1 divided by 1 plus blah 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 is exactly 45 over 89. So this was a rational number, and this expansion here was finite. This was not by accident, but this is more generally the case. Let's have a look at some other expansions. I've written here some lovely numbers, like for example the golden ratio, which is a very lovely continued fraction expansion of 1, 1, 1, 1, 1. Square root of 2 is also very lovely. If we look at other square roots of non-square numbers, they don't look quite that nice anymore, but they're also periodic. So we see here, for example, 213128, 213128, and so on. So this is periodic. Whereas other nice numbers do not have a periodic representation. So in particular, these A and E, the Euler number and pi, they do not have a periodic representation. The Euler one is still very nice, so I hope you can also see a pattern here, whereas pi looks just wild. However, if we look at the pi expansion and cut it off here at some point and just take the first two entries and continue the finer details here, then we get exactly our pi approximation day of 22 July that we saw in the previous slide. So this is apparently an approximation, and if I would go further here, I would get a more precise approximation of my number. And these approximations are called convergence. So if I have some number with a possibly infinite rational fractional expansion, and I cut it off at some point, I get a convergent. And this convergent can then be converted into a rational number, an divided by bn. And I can also, again, compute these convergence quite efficiently, either by doing the steps I said previously and keeping track of everything, or by using this simple recursion. So if you look at the rules you saw on the previous slide and on this recursion, I guess it's easy to follow why this makes sense and why we can in this way recursively compute the convergence of a number. And these convergence are in some sense the best approximation of alpha, the best rational approximation. And in which sense is that? It's in the following. So if I take some of these convergence and the distance between the convergence and the actual number, then this distance is better than any other distance, or is smaller than any other distance from alpha to any rational number where the denominator is at most bm. So if I don't let the denominators become arbitrarily large, then these convergence give me the best approximation I can get within this limit. Okay, this is why convergence are nice for approximation. What do they have to do with factoring? Well, multiple things actually. And one of the things is that they can give us a nice way of finding clever values x squared for our factoring algorithm that we saw. So this is now a different approach to the sieving one we had before, where we always took values x that were close to square root of x. This is a different approach, and it can be very efficient. And the idea is the following. I'm again trying to collect squares that are smooth, and I again try to have numbers y that are very small so that it's likely that it actually factors over the factor base. So this is now another trick, how to find x's with small y's. And it works as follows. We're going to work in the vicinity of square root of n, but instead of just taking the next few and the smaller few integers, we take the convergence of square root of n. And there's actually a very easy algorithm for precisely computing these conversions without the messy floating point arithmetic that would be needed for the previous approach. I'm not going into the details, but you can find it on Wikipedia. So I compute convergence of n. And then, as candidates for the values x, I take exactly the numerators of these convergences that I find. So the part above the fraction bar. If that is the case, then what do I get for y? I take again these values a that I find squared modulo n, and since this is since a divided by b is so close to square root of n, a squared minus n times b squared is going to be very small. So I'm now not subtracting n, but I'm subtracting n times b squared, where b is the denominator of my fraction. And because these a divided by b are such good approximations, these values here are all going to be very small. And more specifically, I can even bound how small exactly those are. But I guess the intuition that they are small is relatively clear. So let's have a look at an example of this. How does it look if I do this in practice? So I'm now factoring some 9072 as my n. So I first need to compute the convergence of square root of n. So square root of n is approximately 95. And if I use the either good floating point arithmetic or the easier algorithm that I linked on the previous slide, then I can find the following first few convergences that approximate this number. First one is quite obvious, it's simply 95 divided by 1. Well, that's a reasonably good approximation. The next one is 286 divided by 3, and so on. And we see that very suddenly the numbers in the denominator actually become quite large and the numerator even larger. So the numbers that we work with are quite a bit larger than those we had in the quadratic sieving. However, if I now do the same thing as before, and I now evaluate a squared minus n times b squared, then I get the following very, very small numbers. So these are now actually smaller than some of the ones we saw before. So we get small negative and small positive numbers. And again, many of them are smooth, can be reduced to, for example, this one is clearly 3 smooth, this one is 7 smooth, this one also only has small factors, and so on. So if we continue this example, we do the same steps as before. I'm not going into the details, it works exactly like before. And again, we can successfully get the number. Because again, from the previous slide, we already got several smooth y values that we can use and then combine cleverly. Okay, so that's it for the standard factoring algorithm. And I want to use the last few minutes for a special trick that also works in RSA, but is not actually a factoring algorithm in itself, but it also uses continuous fractions. And this is Wiener's attack. And it works only under some conditions, but if it works, it's very, very fast. And the condition is the following. It works if the numbers p and q are reasonably close together. And so this is not a real condition. And this is the most important one, if the private exponent in RSA happens to be relatively small. Now people would often be tempted to use small private exponents because it makes all the private computations cheaper. And this algorithm is a reason why you shouldn't do that. Why you shouldn't have small private exponents, where small means less than 1/4 of the length of the full possible bit size of n. And under these conditions, what Wiener found out is that the private exponent d magically appears in the convergence of the value, the public value e divided by the public value n. So if I take the public exponent and the public modulus, take this fraction and compute its convergence, then in one step, the secret exponent will magically appear in those convergence. And the reason for this is, or one of the useful properties for this is, that if we have some value alpha and a rational approximation for this number, and those two are very close together, so the distance is at most 1 divided by b squared approximately, then we can guarantee that the fraction a divided by b actually happens to be a convergent of alpha. So this is a sort of contrary property to what we saw before. Before we saw the convergence of a number are a good approximation, or the best, and now we see if we have an approximation that's at least this good, then this actually must be a convergent. And we're going to do this here by looking at two numbers, one of them public and one of them secret, and one of them is going to be the convergent of the other. And there's now a bit of math on here, don't be disturbed by that, let's go through it step by step. I probably should hide this part for now before we get there. So the first important thing to recall is what was again the relation between the public and the private exponent. The two were inverse to each other, which means that the public times the private exponent equaled 1 modulo phi of n, which means this product minus some multiple of phi of n equals 1. And now we can rephrase this equation a bit. We can divide both sides of this equation by d and by phi of n. Then we get the following here. Then we get that e divided by phi of n minus k divided by d equals 1 divided by d times phi of n. So in other words, this value here is an approximation of this value here. Now this value here is definitely very secret because d is the secret exponent. The thing is, this is half private, half secret. So we do know e, we do not know phi of n. But what we can do is we can approximate phi of n. So what we can do is, we know if n is p times q, then phi of n is p minus 1 times q minus 1. And if I now look at how far these two numbers are apart, if I just fill in the numbers, what I get is that the distance between the two is simply the sum of the two prime factors essentially. And because of the conditions we placed on the prime factors before, these sum of the prime factors is at most 3 times square root of n. This is because the two prime numbers are relatively close together. So we now have 3 values that are close to each other. K divided by d is close to e divided by phi of n, and e divided by phi of n is close to e divided by n, because n and phi of n are approximately close to each other. So that now means that the distance between this public value e divided by n and this secret value here is this plus the distance we get from here, which in total satisfies this bound that we saw on the previous slide between some rational number and its convergent. So we have now found two numbers, one of which we know, which are as close together as the bound on the previous slide once, which means one of the two is a convergent of the other. More specifically, this unknown value here, k divided by d, must be a convergent of this known value here, because the two are close enough together. So what we can now do is we take the public number e divided by n and simply look at all of its convergence until something divided by d pops up, and d can be verified as the private key. So what we do is we compute all the convergence, check each value d that we get, whether it satisfies the RSA equation, so whether it could be the private key, and after not too many steps, we actually find it. So let's have a look at an example. Some very large n, some very large e, and the important condition that d isn't too large. So I can now compute all the convergence of this divided by this. Just filling in the numbers, I get a couple of things near 1. Blah, 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 blah. It goes on and on. And what I now do is I test each of the denominators here, whether it can successfully decrypt something that was encrypted with the public exponent. And once this works, I can be confident that I have found the secret key. And in this specific example here, the first number where it works is this one here, 569. So this reveals, after trying only a couple of values, that the secret exponent is 569. So this is a very clever trick that is very, very fast, much faster than it should be, but that only works if the prime numbers are close together and the private exponent is small. So conversely, this gives us some insight on how we should scale our RSA and what additional requirements we should put. And two of these requirements are: don't make the prime numbers close together, and don't choose a small private exponent. So make sure that it's quite a bit above this bound here. Okay, that's actually already, we're quite good in time. We've now covered, as expected, the factoring algorithms of this first family, which were all about writing things as squares and finding equivalent squares. And next week, we're going to have a look at this second type, which is based on groups, algebraic groups. So I'm just going to skip over this to a final overview slide that shows how fast are actually all these things that we've had a look at so far. So here we are, runtime comparison. So the important thing is that most of these factoring algorithms are written in a very specific notation, because they don't have a simple exponential or polynomial runtime. They have something in between that's super polynomial but sub-exponential. And these are always written in this special L notation here. So the L notation has two important values in here, an exponent alpha and a constant c. And the runtime, the asymptotic runtime, is then as follows. It's exponential in constant plus something that disappears with respect to this constant value, times the following two terms. Something logarithmic in n to the power of alpha, and something doubly logarithmic in n to the power of 1 minus alpha. So what this means is, if alpha is very small, so in particular if alpha is 0, then this part here disappears, and what remains of the runtime is only this part here. So this is log n to the power of 1, and since we have an exponent here in the beginning, this is essentially, so the exponent cancels with one of the logarithms, and what remains is logarithm of n times some constant in the exponent, so to the power of something. In other words, it's polynomial. If alpha is 1, then this part here remains, and this part disappears. So what we have is e to the power of c times log n, or in other words, n to the power of c. Now, since n is exponential in the size of n, this corresponds to an exponential runtime. And if we now look at the algorithms that we discussed today, we see that for most of them, the exponent alpha here, which decides whether it's polynomial or exponential, is 1/2. So it's somewhere in between. And there's a second value which is just a constant, but since this constant turns up in the exponent, it's a pretty crucial constant. So this in practice has a huge impact on the runtime, this constant. So what we see here is that the basic random squares algorithm can be shown to have parameters 1/2 and 2 times square root of 2. CFRAC is quite a bit faster because it has the same alpha but half the constant. So CFRAC is the continued fractions trick that we saw as the third factoring algorithm. The elliptic curve one that we are going to have a look at next week has essentially the same as continued fractions, but not with base n, but with base p. So it's super polynomial sub-exponential in the smallest prime factor of n instead of n itself. So this is faster if one of the prime factors is very slow, roughly speaking, because this is still asymptotic stalking here. The quadratic sieve is even better because it has a constant of 1 here, still with 1/2 as alpha. And the fastest one, the general number field sieve, has a smaller alpha, so it's closer to polynomial, but a relatively large constant. And to give you some feeling about how large this is, if we fill in here 1024-bit RSA key, which is generally recommended for approximately 80-bit security. So usually we want more 2,000 to 3,000-bit keys. If we fill this in here, then the difference between the two runtimes of the general number field sieve and the quadratic sieve aren't actually that massive. So one of them would end up at approximately a runtime of 2 to the 100 and the other 2 to the 120 approximately in the number of operations. So there is again some factor involved here. The important thing is these are both a bit above this normal 80-bit security estimate, and this is for multiple reasons. First, to provide a bit of margin, assuming that the best factoring algorithm is actually a bit faster than those we currently know. And second, it includes a sort of factor that compares RSA evaluations with arithmetic operations, because these runtimes here are relative to the number of arithmetic computations, whereas RSA in itself needs quite a number of arithmetic operations. So if we want to compare, so usually when we state something like 80-bit security, we mean it takes at least 2 to the power of 80 evaluations of this scheme, which is more than 2 to the 80 arithmetic operations. And this is the second reason why the security recommendation is usually a bit lower than the actual runtime we get out here. Okay, finally some words on factoring records. In the past few years this was always very boring because I always had to say, oh, the newest factoring record is already from 2009, very old, not much has happened in the meantime, but things are actually currently happening. So the newest factoring records are just 1 year old, and the one before that just a bit older. So the largest RSA moduli that were publicly factored by research teams were more than 800 bits, so 795 bits using approximately 900 CPU core years. And the other one, 829 bits, was done just last year using 2,700 physical CPU core years. So of course with some parallelization, but it's still a lot of time effort as well. You can read a bit about the research behind this, so both on the optimizations to the algorithm that they used and the efficient implementation in this paper here. And as I already mentioned, maybe we have to update this list soon, but I have my doubts whether this is actually the case. Okay, that's everything from my side for today, and I'd now be very happy if you still have any questions. And of course, I'll also be available afterwards for a moment if you still have anything on Discord. Now I need to go back to the question slide. Here we are. Let's see if there's anything. And in the meantime, thanks a lot for joining today, and I hope to not see, but at least imagine many of you next week. So it looks like not a lot is going on. Next time I'll make sure to enable the questions also during the lessons so that you don't have the opportunity to start typing only after the last lecture. That's of course more clever. Anyway, thanks a lot. I hope you have a nice evening and see you next week. Bye.